Hey everybody, we're going to talk about quadratic and polynomial functions today, and we're going to start with quadratics. And we already talked about that before the last exam, but we're going to start by discussing what most people would call the standard form of a quadratic function. F of x equals ax squared plus bx plus c. So anytime you see a function in this form, you can say, hey, that's a quadratic function. A, b, and c are real numbers, and a can't be 0 because if this term goes away, then we're just left with a linear function. So a is the only one that cannot be 0. B and c could be 0, so this term could not be there, or this term could not be there, and that's still quadratic as long as you have an x squared term and nothing higher than x squared. Higher than x squared are polynomials. Quadratics are a polynomial as well, so are lines technically, but those would be higher order polynomials. That's what we're going to talk about later in these videos. So your book calls this the standard form of a quadratic function. Most people would call this the vertex form because, as you can see, hk, which is the vertex, can be read right off the equation. So you already know what the vertex is. This a value here is the same as this a value here. And like we talked about in the transformations video in the last week's videos, this is the vertical stretch factor and will change the vertical parts of your graph. So normally we go up 1, up 3, up 5, up 7. Now we're going to go up those numbers times whatever a is. And if a is negative, it also opens down. Okay. The axis of symmetry is always going to go through the vertex, but more importantly, the x-coordinate of the vertex. And so x equals h is always the axis of symmetry. And it's really, when we were drawing those quadratics, we knew there was symmetry. And so we're going to start drawing in that invisible line on the graph. Okay? So again, if you see standard form, that's your book telling you this form right here, which is what most people would call vertex form, but if you see standard form, this is what they're talking about. So we're going to start by writing an equation in standard form. We're given the vertex, negative 3, 4, and we're given another point that the function goes through. Okay. So, standard form, let's just write it down. This is what it looks like. Notice how the negative is built in to the equation here. And so, since this vertex has an x-coordinate that is negative 3, this is h. h is negative 3. And so, we have an x minus a negative 3, which I'm going to write as x plus 3 squared. And then k is 4, and the plus is there, so that's just plus 4. Plus 4. And then we still have this a value that we need to find. So what we can do to find that value is we can plug in a point. So we have another point here, negative 4, 7. So 7 is the output. Negative 4 is the input. Don't forget about the squared part here. So negative 4 plus 3 is negative 1, but when I square it, it becomes positive 1. So this is 7 equals a plus 4. So that means a equals 3. But I'm not done yet. We need to find the standard form of the quadratic function. So I found a, I know h and k. Now I have to put it all together. So f of x is going to be 3 times x plus 3 quantity squared plus 4. And this is my final answer. Again, I need the variable x to be in my final answer. I'm not going to leave it here and plug in what a is because then I have a singular point plugged in. This is just a true statement. If I put 3 in here, I'm just going to get the same value on both sides of the equation. I want a function that represents every point that would be on this graph here. Speaking of graphs, this is something we should know how to graph, because we know what x squared looks like. This is shifted 3 to the left, 4 up, and there's a vertical stretch by a factor of 3. So all my vertical movements are going to be multiplied by 3. So instead of going up 1, 3, 5, 7, we're going to go up 3, 9, 15, 21. And then this also asks, does f have a maximum or a minimum value? So they're basically, when you see that question, max or min, it's asking, does this parabola open up or down? So a max would be if I was opening down, it has a maximum value, and that value is the vertex. If it's got a minimum value, that would be if the graph was opening up, and that minimum value would also be the vertex. And so in this case, the maximum value is not in play. There is no maximum, because this opens up, which I can tell from my a value here. It opens up, and so we would have a minimum value, and that minimum value is actually this one here, 4. Because the value that they're talking about is the output. So the minimum value is 4, and it happens when x is equal to -3. So let's go ahead and graph one of these just to refresh our memory. This one's pretty similar. And again, our basic quadratic equation starts at the vertex is at the origin, and we go up 1, out 1, up 3, out 1, up 5, out 1. And this is my basic quadratic equation graph right there. So this is x squared. Now, what I could do here is I could take this right here, and I could move it around, right? So this is saying move it 3 to the left and up 9, but then it's also telling me that this should be opening down and it should be stretched out. It should be stretched out. So this is the starting point of my new quadratic. It's going to be right there, which also means that the axis of symmetry, oops, I moved that 4 to the left. Okay, so 3 to the left, up 9 would be right here. So this is going to be the vertex of my quadratic. And so the axis of symmetry would go right through it here. So left 3, up 9. Left 3, up 9. And then from here, I would normally go up 1, out 1. The out 1 is not changing. There's nothing in front of this x to change my horizontal movements. So it's just my vertical movements that are going to be changed. So instead of going up 1, I'm going to go down 3. 1, 2, 3. And I'm taking the 1 that I would normally go up, I'm multiplying it by -3. So I'm going down 3. And then I would normally go up 3 after going up 1 and out 1. So I'm going to take that 3 and I'm going to multiply it by -3, which gives me down 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And out 1. The out 1 hasn't changed. And then I normally go up 5 after that, so I would go down 15, which is not going to fit on my graph. But I would go out 1, so I want to make sure I don't flare out down here, because I know that if I go down another 15, I'm still only going over 1. So I shouldn't pass this line horizontally as I go down. So as I'm coming down here, I shouldn't pass. I should not be doing that. Okay, so just keep that in mind. So as we draw this, we're coming down, we're going through this point, but then I should get to the bottom of this graph without having crossed this barrier here. And again, on this side, same idea. And again, it doesn't have to be perfect, but we should be aware of these things as we go out. Like I shouldn't get lazy at the end here and just let this extend anywhere. Okay. So there's the graph of my quadratic, and that's just a little bit of a review of transformations. But what we're going to do in the next video is we're going to graph a quadratic that isn't in what your book calls standard form. Instead, we're going to graph something that's in this form, which most people would call standard form. But this is just what your book calls a quadratic equation. So stay tuned in the next video.